welcome to the class of material selection for mechanical design, and we are in week 2, module 2. We are talking about mechanical properties of materials, and this is lecture 6. So, let us look into the mechanical properties of materials. Earlier I have just touched the point of the Hooke's stress, that actually the Hooke's law that actually talks about the stress to strain relationship, and now if that Hooke's law is to be expanded further, because we have only thought of uniaxial stress to uniaxial strain relationship, but in reality stress is not actually uniaxial. As you can see in this particular case here, that there are such stresses, for example, sigma yy or sigma zz or sigma xx. Okay. So, there are these 3 axial stresses are directly possible. Similarly, there are these shear stresses sigma xy, sigma yz and sigma xz or sigma zx. Okay. So, like that, if I have these other components of stresses also, then we need to express the generalized Hooke's law, where we need to express the stresses in terms of a stress tensor. Okay. So, that is what we have done here, that the stress tensor, the diagonals are all the stresses along the axial sort of expansions, and then the off diagonals are all shear stresses. Okay. So, together this creates a stress tensor. Now, a formal definition of tensors is that we first of all define the tensors in terms of an order, and that is in terms of the number of directions that is required to describe it, right. So, if something is of rank 0, okay, then we will call it scalar. Okay. For example, weight, okay, or so to say the mass. So, that is a scalar. So, that is of one component only. Now, if you have to have a magnitude as well as a direction, then it becomes rank 1 and then it becomes a vector. Okay. So, we know that the force itself can be a vector. Okay. So, we always write that force as Fx, Fy, Fz. Okay. So, this becomes a vector. Okay. Similarly, the moment can also be a vector, but then there are for a plate, then you can also have the other moments and twists together would not be a vector. Otherwise, simple direct moments can be expressed in terms of a vector itself. But if you want to consider the twists together, then of course, you have to express it not just a simple vector, but with a higher dimension. Now, then the higher is form of vector will be dyad, okay, that is rank 2, that is where you have magnitude and 2 directions associated with it. Okay. So, if you for example try to define the state of stress at a point, so what do you need? You not only need the force itself, but also you will need the area that defines the force. Okay. So, you need magnitude and 2 directions. Okay. So, for example, if it is an axial force, then in that case the magnitude of the force and the direction of the force that is that is important, and the area normal to define that which way the force is applied. If it is a shear force, then it is with respect to the parallel surface, okay, of it. So, then the area, corresponding area, actually the area normal itself will be different. So, thus you need actually always to define the state of stress at a point, you need 9 components, and that comes under the dyad. So, that is 3 square or the 9 component system. Then of course, there can be higher orders in terms of triads and other things, but for mostly our applications we will keep ourselves up to the dyad level. The triad level where it will be important, well, higher level of things will be important when, let us say, I am taking a relationship between two dyads, like your stress is one dyad and your strain is another dyad. So, when you are finding out the elastic constants between the two dyads, then you are going to a higher order tensor. Okay. So, then you need not only I j k l, but all of them together. So, all I j k l's together, and then that would become 3 to the power 4. Okay. So, that would then become 81 components for stress to strain. In fact, for any generalized stress strain relationship in the Hooke's law, you will need 81 components to define the relationship between stress and strain. Okay. Well, now the other important thing I already talked about is the Poisson's ratio, and which is nothing but the negative of lateral strain to tensile strain. Okay. Assuming that you are extending in one direction, so the other direction it is going to sort of get narrowed down or contraction, then the ratio, in order to keep it always positive, we take the negative of it. In fact, when people defined it, they had no idea that there can be systems which will go just the other way around. Okay. So, I just give you one very simple example, but today there can be synthetic systems where Poisson's ratio can be negative. Okay. So, suppose you have this type of a system and you are applying the force. Okay. So, what will happen is that this is gradually going to get opened up, and as a result of it, it is going to have not only expansion in this direction, but also expansion in the other direction. So, this is going to have a negative Poisson's ratio. The reason, because we already kept that negative sign for the cases which generally happens that the things narrows down. Okay. You can also get in nature materials in which case the Poisson's ratio will be 0 in the sense that it is not going to actually deform to the other direction, and this champagne bottle cork is one such example. Okay. So, which is important because that actually keeps it continuously pressurized and it does not sort of in the perpendicular direction, it does not give up. So, the ceiling is always maintained. So, that is the case up to 0, but then you can have the negatives also, as I have just now shown you. Usually the Poisson's ratio usually remains between 0.25 to 3.3, for cast iron 0.23 to 0.27, concrete 0.2, rubber has an unusually high Poisson's ratio, okay, of about 0.5. So, that is the sort of the maximum Poisson's ratio that you will generally get. Cork, as I told you, is nearly 0, and novel foams are this type of foams, in which case the Poisson's ratio could be negative. So, other mechanical properties, the Poisson's ratio plays a very important role. And now, let us take a look back to our Hooke's law. Okay. For an axial case, we know sigma equals to E epsilon. So, that is how the modulus of elasticity E, the Young's modulus we always use. And then for shear case, we have tau equals to G gamma, and for the volumetric case, we have pressure part that now comes into picture. Okay, the volumetric pressure that is coming, and then that equals to minus of K, and then the change in the volume over the original volume of the system. Okay. So, this is typically because we have defined all this system keeping tension positive, whereas in the last case it is actually compression. So, that is why we keep the minus sign, so that the material value always remain positive. Now, these are all related, E, G and K for materials, they are related. So, I will come to it in a minute. So, this is just showing you that what is the modulus of elasticity range that you can expect Okay. Highest in this direction will be for materials like diamond, materials like tungsten, alumina and all these things. So, that would be the highest, and then of course, the more usable group will be somewhere here. Okay. Iron, steel, titanium, aluminum. So, these are more usable groups, okay, in terms of the metals, which has something like 2 to 500 gigapascal modulus of elasticity. And in the lower range you have the polymers, and that is approximately in the range of 1 to 2 gigapascal, except some polymers which has a relatively higher modulus of elasticity, and rubbers of course have very poor modulus of elasticity, and composites, the sky is the limit, because you have CFRPs which are as good as some of the highest modulus of elasticity, and then you have GFRPs in the mid range, and you have wood type of composites which will be as low as the polymers. So, that is the entire range of possibilities of Young's modulus in the polymer. And in the of course, the room temperature, because this all these properties vary a lot if you go to a low temperature level. Okay. So, in the room temperature, the elastic shear moduli and the Poisson's ratio for various metallic alloys, which are generally important for us, we have to just keep them as a thumb rule. Some approximate ideas like aluminum, like brass, copper, magnesium, nickel, steel, titanium, tungsten. Okay. So, that we have to keep in mind, and as I told you that this G is related to E, as G as E over 2 into 1 plus nu. So, if you know what is the general range of Poisson's ratio, you can approximately find out what will be your shear modulus. Okay. So, knowing E and knowing nu, you can get the G, and then you do not have to keep too many things in your mind, but at least the E and the ratio, Poisson's ratio will be important for you. Now, one important group, as I told you, for the strength group, we actually carry out these tests in a tensile testing machine typically, and then from that we can get the ultimate tensile strength, percentage elongation, Young's modulus, all of them. Okay. So, in fact, these devices are called universal testing, tensile or compressive testing machine, and because of that it is also known as universal UTM. Okay. Now, what are the things that we can get? Okay. First of all, if you carry out these analysis by applying loads on a system and studying how the deformation is taking place for metals. So, this please keep in mind that this is typically for a ductile. Okay. So, this is typically for a ductile metal. Let us write it here as a ductile metal. Okay. For such a system, you would see that initially in the stress strain diagram there is a linear region. So, this is almost linear. Okay. So, the yield strength is defined with respect to this region itself, and however, this region has some part, you can see that this up till this point there is linearity, and then this little bit of it that is nonlinear. Okay. So, this part is nonlinear, and yield strength is defined in a way that if you remain below this region, then whenever you are unloading, you are going to come back to 0. Whereas, if you cross the yield strength level, then actually the plastic strain starts to accumulate. Okay. So, here the significance is that if you take your load beyond this level, then actually two things can happen. One is that for brittle materials there can be a fracture that can happen. Okay. Whereas, for most of the other materials it may still deform for a little larger time, and that is entirely inside the plastic strain domain, until and unless the necking starts to happen. Once the necking happens, in all practical sense the material is irrecoverable and the failure is going to happen. So, that is how the ultimate tensile strength is always defined when the necking starts. Okay. So, that part beyond necking, actually the plastic deformation itself becomes non-uniform in nature. So, you see that in this stress strain diagram you get so many information, right. You get first of all this ratio in the linear domain, and that will give you the modulus of elasticity. So, the slope, you are going to get the modulus of elasticity, and then you are going to get the strength information, the yield strength, okay, beyond which the plastic deformation is setting in. Okay. So, that is the yield strength point, and then you are going to get the fracture strength in some cases, but for ductile material you are going to get the ultimate tensile strength. Okay. So, all these things you are going to get, and also keep in mind that this is a typical stress strain diagram, which may be also called as an engineering stress strain diagram, but there is a true stress strain diagram where actually this this sort of decreasing would not happen. Okay. So, you will see that it is actually calculated on the basis of the actual area of deformation. So, that we will look into it very soon. Now, the stress and the strain, I already told you that the percentage elongation. Okay. So, for a metallic system we generally keep the 0.2% strain, or epsilon equals to 0.002 as the value which is more or less the elastic offset. Okay. So, beyond which the plasticity happens, that is a sort of a thumb rule. So, you can see the 0.002 value here plays a very important role, that 2%, 0.2%. Now, of course, for rubber or such polymeric systems, elastomers, this can go up to 10%. Okay. But these are different types of, that is why I said that this is mostly for the ductile metals. Now, I told you that in engineering stress strain curve, okay, so that the stress drops down after necking. We saw that the stress drops down, right. But actually if you test the area at that point, you will see that the area itself, because of the necking, is coming down. So, as a result of that, you will see that the true stress is actually increasing. Okay. So, the stress is not coming down, that is a fallacy. The stress is actually enormously increasing, and then because of that finally the failure happens. Now, this part the plastic deformation part can be modeled with the help of a power law, okay, and where the K is the strength coefficient and N is the strain hardening exponent part of it, and N equals to 0 for perfectly plastic, N equals to 1 for elastic. For most metals, the value of N is between 0.1 to 0.5. So, that is the flow or curve of the material at the plastic zone itself. Okay. So, that is one point we have to keep in our mind for the stress strain diagram, that whether we are plotting the true stress strain diagram or we are plotting the engineering stress strain diagram. So, if it is a true stress, then of course, it is load over the instantaneous area, the area changes, and so it will come out as sigma times 1 plus epsilon, and where sigma and epsilon are the engineering stress and strain. So, once you get the engineering stress and at a particular strain, then you have to get the true strain by multiplying the stress with 1 plus that strain. True strain, similarly you have to actually integrate this entire thing, okay, as bit by bit, and you are going to get these in terms of log of 1 plus epsilon. Okay. So, thus you can get the engineering strain from the true strain by actually doing the reverse operation of it, but that is the way the true strain and the engineering strain are related. So, one important point we have to keep in mind, that while deriving these, one thing we kept constant, and that is that the volume is constant. Okay. So, if the area is changing, along with that the length will change. So, the A0 L0 will be equal to AL. That constancy actually during the neck formation onwards, that gives us this relationship that between the true stress and the true strain. Now, I told you that stress can be, stress and strain relationship can be thought of in a different uh, uh, way in terms of the mathematical relationship. Most of the times it depends on the nature of the material. If a material is homogeneous, that would of course mean that these properties are not going to vary from point to point. Okay? So, something like a composite, where from point to point these properties are going to vary. Whereas, if it is an isotropic material, that means in a particular direction if you go, the property are not going to change. Okay? So, it is going to change from direction to direction, not from point to point. So, that is the difference between homogeneity and isotropic situation. So, if you have both homogeneous and isotropic, then of course, the properties will be independent of the location and the direction. And there are some cases where it will be an orthotropic material. So, that means you will get different properties along the orthogonal directions. The modulus of elasticities will be different. So, you see that if it is a homogeneous isotropic one, then defining one single modulus of elasticity like Young's modulus would do. Okay. If it is a orthotropic material, then you will need E1, E2 and E3 at least. Okay. Most of the times it is E1 and E2 that should do. And if it is not like that, any other generic material, then you will be having so many other different elastic constants for each of the cases. So, depending on what type of material we are choosing, the nature of the material, okay, we will see later on that, for example, if you go for a metallic system, they are generally homogeneous and isotropic. That is the advantage to deal with such a system. You do not need too many constants to define it. On the other hand, if you go for a composite material, it is highly anisotropic in nature. You can at best make it orthotropic. So, still the properties will vary with respect to the direction, and you have to take that additional care while defining the material. Now, I told you that these modulus of elasticity, the Young's modulus, the shear modulus and the bulk modulus, they are related by some simple relationships like the G is E by 2 into 1 plus nu, and also that equals to 3k over 1 minus 2 nu. And in fact, if you do a little bit more, you will see that E can be defined with respect to k and G as well. Okay. So, we can interchange. And that is why the key thing is that you need to know from these relationships. Let us say I have to evaluate G, I need to know at least E and nu. Okay. I need to evaluate K, I need to know at least E and nu. So, this is the benchmark with respect to which we can do it. In some cases, if say you do not know the Poisson's ratio, then and you want to evaluate E or K or G, then in such a case you need to have at least two of them with you. For example, if you know K and G, you can use this relationship to get E, and again in a similar manner you can do the algebraic manipulations to get K from E and G or G from E and K. Okay. So, that is the case where Poisson's ratio you are unable for some reason to determine. Now, another important thing now is a very important thing, that if a material is linear, elastic, isotropic and homogeneous material, then number of elastic constants required to define the stress strain relationship will be only 2, right. That means maybe it is just E and nu or G and nu, etc. If it is fully anisotropic, I told you it will be relationship between the two dyads, and then you will need 81 constants. But luckily some of the shears are complementary and they are equal. So, one can show that in general you will need 21 independent elastic constants, and if it is perpendicular directions, if there is a symmetry, then you will need only 9 independent elastic constants. So, your gradual requirement of defining the material property will come down depending on the homogeneity and isotropy of the material. Now, from the stress strain relationship, not only we can conclude on the modulus of elasticity and the other strength properties, yield strength, ultimate strengths, etc., Poisson's ratio, but not only that, but also some more interesting things. For example, the ductility, that means measure of the degree of plastic deformation that has been sustained before the fracture occurs. Okay. So, that is a measure of that how much you can really deform a material. See, many times we actually use these for drawing wears, for example. Okay. So, how much it can do before the wear actually breaks. So, ductility is a measure of this kind of things. So, this is important because ductility talks about all this plastic deformation that it can sort of withstand before the failure. Okay. And then the other property is the brittleness. Now, brittleness is of course that it is related to the failure, and that failure is generally not in the plastic domain at all. As I told you that how far you can go for a material in terms of the yield strength, that is the level of the brittleness of a material, because some materials show that the failure strain is very, very low. Okay, you cannot really take it like a ductile material. So, such materials, if they are used along with a ductile material, you can make a nice composite out of it, because you see the good side of a brittle material is that their modulus of elasticity, if you compare the slopes, their modulus of elasticity is much higher. So, you can use a brittle material with a ductile material in order to get an overall gain in terms of a composite material. Now, how do I physically locate? Well, ductile materials generally you will see you will have a cup and cone formation, whereas for a brittle failure it is like a flat surface. Okay. So, that is a telltale sign of identifying whether from the failure whether it is a brittle material or a ductile material. A very important property I will tell you related to this stress and strain is the resilience, that is the amount of energy that you can absorb elastically in a system. And there is a modulus that we keep for it, which is called modulus of resilience, and that is the strain energy per unit volume that is required. So, if sigma y is your yield strength, then till that point the material is elastic. So, in the stress strain diagram, this entire area gives us the measure of modulus of resilience. The larger it is, the bigger will be the modulus of elasticity, the modulus of resilience. And the way you can measure it is by approximating this with respect to half sigma y epsilon y. Okay, this is not you are still leaving some area out of it, but approximately half sigma y epsilon y, or in other words sigma y square over 2e. Okay. Some materials have a very high resilience, for example, beryllium copper, and they have very good spring like applications. I will show you through an experiment that how the resilience can be directly observed in terms of while you are falling an object. Okay. Now, we are coming to toughness. Toughness is similar in terms of energy absorption, only thing is that it is not in the elastic domain, it actually contains the entire domain. Okay. So, that is energy, the entire energy that you can absorb up to fracture, that is the measure of toughness. Okay. So, that is why that is the difference between the resilience and the toughness, that resilience is only concentrated on the elastic domain, but the toughness considers the plastic domain also. This is important when you are absorbing some energy from impact, for example, how much of impact you can sort of resist. Now, to do that you can do a test which is also popularly known as Izod impact test. So, what you do here is that you create a material with a notch, and then you hit a hammer from the back side and you can actually vary this angle. So, through that total impact you can change, and by putting a V notch on the material and then placing this pendulum to hit it from the back, you can see that how much of impact it can withstand in an ISOT test. So, that is one way of measuring the impact strength of the material. Okay. So, the other way of doing it is a Charpy test. For a primary difference of Charpy test and ISOT test is the support part, because for a Charpy test, as you can see that the support is here, the notch is here, and you are driving it this way. Okay. So, that is for a Charpy test, and if you look at it for a ISOT test, the support is here and you are hitting it in this direction. So, this is the difference between the Charpy and the ISOT test, but both of them essentially measures about how much of impact, or in a way what is the toughness of a material. Okay. Now, Charpy test is generally used for polymeric materials, whereas ISOT test is generally used for metallic systems. So, this is some of the Charpy and ISOT impact test and the typical measure of toughness, and you can see that metals are invariably in terms of toughness they are in the top. Next to that, some composites come up, okay, and then the worst are possibly the ceramics. Okay. So, what are the factors that affect the impact energy? Well, for a given material, the impact energy will decrease if the yield strength is increased. So, there is always a trade off, a give and take type. Okay. So, on the other hand, if you want to increase the yield strength, maybe for applications where you do not expect an impact load, it will be good. But if there is an impact there, something falling, then it is always noted that if the impact strength is increased, then the impact energy for a given material is generally decreases. The notch serves as a stress concentration. So, whenever you have a notch, that reminds you that that is the area where it will be most sensitive in terms of the failure, and most of the energy is absorbed by means of plastic deformation. Okay. And that is why factors that affect the yield behavior, like ductility, okay, of the material, temperature, strain rate, they all play an important role in terms of the impact energy. So, we will complete at this level for this talk, and in the next lecture we will talk about hardness, creep, damping and fatigue. Thank you.